Hey everyone, so in this video we are going to start with the TensorFlow. But before we begin that discussion, we need to understand why TensorFlow. So a couple of things. One is that whatever deep learning models we build, they involve a lot of matrix multiplication. And matrix multiplication with increasing size of data, with increasing number of layers in our neural networks can be pretty expensive. And doing all of them in CPUs causes the overall training process to be slower and slower and slower, and many at times it might not even be feasible. So one thing that TensorFlow brings to the table is enabling us to work with GPUs, okay, among other things. Of course, a lot of optimizers that we need for deep learning, a lot of different kind of architectures that we learn going forward are available as pre-built in TensorFlow. But the most basic thing that TensorFlow does to make the overall process better is to bring in libraries which can make use of GPUs. Second thing is what do we expect from TensorFlow to have? For that, we need to understand what do we need in deep learning models themselves. We saw that overall we build some kind of cost function and we calculate its gradients. We update or initialize our weights randomly and update them using this idea of gradient descent. Of course, there are multiple different alternatives to this. This is gradient descent, then we have stochastic gradient descent, which instead of working with the entire data, works with random subsets of it and calculate gradients for them. Then we saw other variations of the gradient descent, that was RMS prop or gradient descent with momentum, and amalgamation of both being Adam optimizer. But the basic idea remains this, that if we have some framework which can let us calculate gradients of any generic function, that will be great. Now, when we are building cost function, there are two kind of data that we are working with. For example, let's say for a regression problem, my prediction function is fx equal to beta 0 plus beta 1 x1 plus beta 2 x2, or more common notation that we will be using throughout in deep learning will be talking in terms of weights or using the symbol w. Just changing the symbol doesn't do anything, the process remains same, but however, just to keep you more tuned to whatever notation we are going to use forward, we'll call them w's. When we use this to build the cost function, it's going to be yi minus w0 minus w1 x1i minus w2 x2i whole square sum over all the observation. This is going to be the cost function. So there are two kind of numbers we have here. One are these are observed data points. So as such, for a given fixed data, these are going to be constants. However, the parameters w0, w1, w2 and many more, if the neural network is more complex, you will have more number of parameters. But as such, parameters and the real data on which we are building the model for are going to be two numbers that we are going to deal with. So these are going to be largely constants, as I mentioned. These are constants. There are going to be other kind of numbers, these parameters, which are going to be variable in the sense that we will initialize them with some numbers and then we would like to update them using these gradients. Okay, so these are going to be variables which might start with some value, but over time in different steps we would like to update them, reassign them to some updated values. And these are two kind of numbers that we expect from TensorFlow to support. Okay, so with that thought, now that we have clarity about expectations from TensorFlow, that is, it should be able to support these two kind of numbers, that is constants and variables, and given any generic function, it should be able to give us gradients. That will form the basis of the entire platform. Of course, In more complex workflows, we would also expect TensorFlow to have pre-built libraries for different kind of optimizers, for different kind of complex architecture layers. But these are the basics which will form the TensorFlow, and that is what we are going to discuss today. Let's start with TensorFlow. Import TensorFlow SDF. Those who are working with their own local machines and are facing some issues with TensorFlow installations, or going forward simply facing issues that they do not have GPUs on their machines, we will also have a separate discussion on how to work with Collab. That is the cloud platform which Google provides for free. So I'll have a separate video on how to work with collabs in the same section. You can look for it. It's not dependent on any of these, just to work with another separate platform. Okay, you can continue with this discussion without having to go through that. You can watch that separately if you want to work with collab, that is. Okay, so first starting with what are those two different kind of numbers that TensorFlow supports, how to create those kind of data, those kind of numbers, those kind of objects. To create constants, you simply write tf.constant. If you look at these, everything else is same as the way you would written a equal to 4. You see that the value that is stored is 4. However, they are called tensor in TensorFlow vocab. Tensors are nothing but a very broad definition will be a multi-dimensional matrices. So a single dimensional tensor will be a scalar. A two-dimensional tensor will be a matrix, 2D matrix that we are familiar with. The more dimensions will be three-dimensional tensor, four-dimensional tensor, column matrices if you want. Just that these so-called tensors come with their own properties implemented in TensorFlow, which we will get familiar with as we move forward in the course. Okay, so B here also is a tensor, contains the value 2. You can do any kind of operations on these tensors, what we have been familiar with. So A into B is 8, 8 divided by B is 2, A to the power B is 16, and so on. So you can do these different kind of algebraic operations. A minus B is this. The result of these, as you can see, are also tensors. So far, although we created A and B as constant variables, we don't see any difference as such, right? So let's see. First of all, see whether what is so special about this variable guy. Let's look at a result. We will save the result of A into B here, and if you notice, C is not a variable anymore. So we can't really do updation to this variable that we were discussing about, that we can create some numbers and we will update them later on. If we do something like this, it doesn't remain a variable. So if we do A into B, or maybe B plus 2, and if I look at this result again, this is not a variable anymore. So probably this is not the way of updation which will work, which we have been familiar with. The way you update a variable, you simply reassign to the updated value, but that is not how TensorFlow variables behave. So let's create this guy again. Few more examples. Whatever numeric operations that you do, they're not variables. Okay, so starting with this, B is a variable. How do we change this? We change them using a special function, or a couple of special functions, that is. So B dot assign, it reassigns to some other value. Now if I look at B is now 10, and I did not have to write B equal to 10. That will make it not a variable, right, as we have seen. B dot assigns it to now a new value which is 10. B dot assign adds to the existing value. So if it is 10 earlier, B dot assign add has made it 12. B dot assign sub will subtract the value. So now it is 12. If I write assigns of 4, it makes it 8. You also need to notice that this is making in place changes. B has now value 8. Many at times, although right now it might not be very apparent, but many at times we want to do some numpy operation on these tensors. It's not necessary that all the numpy functions will be available to these objects. These are essentially tensors, so they have access to tensor functions. But if we want to do some numpy operations on these numbers or matrices or arrays, we would want to extract the numpy objects from these, and you can simply do that by writing a tensor.numpy. And now we have raw numbers, and you can do whatever numpy specific operations that you want to do. As I said earlier, that right now it's not apparent. Whatever numpy operations or numeric operations that we were doing in our raw Python, we are able to do that them on tensors also. So you don't achieve much by extracting these numpy values. However, the syntax remains same, and the usage of this will become more apparent as we work with higher dimensional numpy arrays. You can do all sorts of creation of tensors the way we are creating multi-dimensional arrays in NumPy. You can do linear algebra operations like matrix multiplications or getting inverse of matrix with tensors. Let's see some examples. So here, out of 6 numbers, I'm creating a 2 cross 3 tensor. Here it is. So you can see here, if I want, I extract the NumPy 2-dimensional array also from this. This here is a 3 cross 2 tensor. The way matrix multiplication happens, if you want to make use of this symbol which works with NumPy also, for matrix multiplication add symbol, I can do that, or I can use Tensorflow.matmul to multiply 2 matrices. As such, in efficiency there is no difference. This operator a at b, when you are using with tensor, calls this function matmul at the backend. So it's up to your preference, whatever you want to use, the symbol at or tf.matmul. In practice, you will see a lot of people using tf.matmul. So in terms of aligning your code with the majority of people, you might want to make use of the function explicitly rather than the symbol. But as such, in the result, it won't make a difference. Now, of course, you cannot really do multiplication with 2 matrices if their dimensions don't align. For example, you cannot multiply a 2 cross 3 matrix with a 2 cross 3 matrix, right? You can only multiply a 2 cross 3 matrix with something which is 3 cross whatever. So these sidewise dimensions should align. But let's try to do that anyway. B now is a 2 cross 3 matrix, and if I do this, I get an error that matrix sizes are incompatible. You cannot multiply a 2 cross 3 guy with a 2 cross 3 guy. Okay, so well, let's see if the same behavior is seen at tf.matmul. It turns out yes, because as we discussed, that at operator at the backend is nothing but calling this function. So one way is to calculate the transpose first. So there are 2 ways in which we can do transpose. We knew that NumPy transpose is nothing but simply doing b dot capital T. So on the tensor itself, if I try to do this, I get an error that this has no attribute T. So I can do this b dot numpy dot T, and maybe then I can do this multiplication. So a at b dot numpy dot t. I can do that calculation now. There is another function that I've mentioned here. I can convert it to a tensor again, tf.convert to tensor, because the result is a numpy array, and then do the same multiplication. If I want to use TensorFlow itself instead of going back to the NumPy part of the object, I can use TensorFlow's linear algebra module. So tf.lin.alg, lin.alg is short for linear algebra, dot matrix transpose will give you transpose, and if I want to do that multiplication, matrix multiplication, I can do that here. Now here, one quick thing that you should know about is that in this case we are creating a transposed object, and then we are doing this matrix multiplication. Instead of doing that, there is this option in MathMul itself where I can pass the original tensor, and if they are not aligned and I want to do the multiplication, I can specify which matrix needs to be transposed. So in this case, B here, that does not mean the object name needs to be. The second one is being referred to as B. So if I write transpose B equal to true, again you get the same result. Whereas without this option, you would have gotten the error, that is the dimensions are not aligned. So without having to change B explicitly, I can use the option transpose B equal to true, and I will get the result. You can calculate the inverses also. Just you pass the matrix and write linear algebra dot inverse, and you get the inverse. Although just for the completeness sake, I told you that you can do different kind of linear algebra operations, but I don't think you will really need to do this per se in the course itself. The last thing that I want to talk about in this video is the gradients. So let's define any function, and we'll see how to get the gradients from Tensorflow. A very nice function called gradient tape is what we'll be using. So this is some function x squared plus 2x plus cos x. And just like math library that we have in Python, or Numpy library that we had with Numpy, all the math functions were available under Numpy. Similarly, Tensorflow has its own math package. So I can call them using tf.math.cos, and if there are multiple values in that tensor, then cos will be applied on each individual values, just like the Numpy math functions worked. Okay, although those were directly np.cos, here it is not tf.cos, it is tf.math.cos. The syntax is slightly different. These functions are inside the package math, which is sub-package of Tensorflow, and I can call this function to evaluate these values. To understand how gradient tape works, so here is what you need to do. This gradient tape guy needs to look at two things. First, what is the outcome? What do you want the gradient of, right? So in this particular case, I want the gradient of fx, right? So I will write y equal to f of x, where x or if it has multiple inputs, these need to be variables with respect to we can get the gradient. Okay, that's it. The way you can give the object access to this function for which I want to gradient is like this. With tensorflow.gradient tape, it's a function, right? So these parentheses are important. As g, I could name it whatever I want. With the same object name I will be able to access the gradient. Now, as I said that this needs to be a variable, let's make it a constant. Let's see what happens. So I am making it a constant. If I do this, you see here there is no gradient. In fact, if I try to print a, it comes out to be none. Sorry, print a, it comes out to be none. So in order to calculate gradient of a function with respect to anything, that with respect to guy needs to be a variable. Okay, fine. So let's create a variable then. Now you can see that the gradient of y, which is nothing but fx here, I have written a separate function for it. You could have directly written this here also. It doesn't really matter. Okay, instead of writing a function separately, you can do this like this, and we will still get the gradient of y with respect to x at a fixed value. So you need to understand that this function is not, the gradient tape function is not going to give you the mathematical analytical formula for the gradient. For example, the function here is x squared plus 2x plus cos x. The outcome of gradient tape, it is not going to be 2x plus 2 minus sine x. No. You can evaluate the gradient at any given point. So in this case, I am evaluating the gradient, which I am saving it in A, I'm evaluating the gradient of y at x where the value of x is 0. Okay, one thing you will notice that most of the time these tensors will stop supporting operations if the data or the numbers are not 32-bit floats. Maybe in later version of TensorFlow this will be something which is internally handled, type changing, etc. But for now you need to be in many cases make it explicitly 32-bit floats. And I think as you progress in the course and you see more and more errors related to this will make more sense to you. But for now, yeah, take my word that we need to work with 32-bit floats wherever we can. One more thing, that if I now try to call this again, so I have called this once, and let's try to do this again, and you see this gradient tape.gradient can only be called once on non-persistent tapes. So it turns out I can only call it once, and I will have to do this all over again. I'll have to run this line of code again in order to call this gradient again. So every time I want to have access to the gradient, I need to run these lines again. And if I try to call it again, I get this error. Okay, so let's say I wanted to calculate gradients of this function at multiple values, at x equal to 0, 0.5, 1.0, 1.5 and so on, essentially in intervals, and I want to see how the gradient looks. In that case, I will have to write a for loop where this bit of code goes inside the for loop, so that this is being run again and again inside that for loop for every iteration, so that I can access it again and again. Okay, so here I am going to start with xvals equal to an empty string. I'm going to start at value 0 of x as a variable. I'm going to also store how the function looks like. So if I am looking at a gradient, I also want to look at what the function values were. And in this list, I'm going to store all the gradients. And I'm going to look at 100 such values. I'm going to do this operation for 100 times. Okay. And it doesn't really matter what I call this iterator. I don't know, let's call it I. Maybe you get confused with a because I was calling the output of gradient as a. So we'll call it I. For I in range 100, I'm running this again and again. So for every iteration I run this, I update the value of x because it's a variable. I am adding 0.5 every time I go this iteration. And I'm appending the numpy value. I don't want to store the tensor numpy values. Then I'm appending also the function value, that is I'm calling fx and then extracting the numpy value and appending it here. Then I'm also calling the gradient of this y, which is nothing but fx with respect to x, and this will change as every iteration I'm updating value of x. These gradients will also be at the updated values. Okay, and I'm storing them. Let's try to visualize these and see whether it is really doing its job. So the function looks like this, although since I'm not looking at in a microscopic fashion, but it's not very smooth function. There are variation because of that cos x fellow, and it will be apparent when you look at the gradients. You can see here how cyclic in nature they are. So the gradient of this function that I've written is so the function itself was x squared plus let me see, x squared plus 2x plus cos x. Now the gradient of the analytical gradient of this function is 2x plus 2 minus sin x. So without this guy, if cos x wasn't part of this, the gradient would have simply looked like this, y equal to x plus 1, so something like this. But because there is a sine component, cyclic component, the gradient is going to look somewhat like this, and so on. So that is what you see in here. Okay, so a straight line plus added the sin x part. So that tells me that yes, gradient tape can do its job. I can find the gradient of any function using this. Okay, and that kind of gives us all the tool for implementing our own deep learning estimation of parameters, deep learning models in general, because that is all that we need, right? I can define a cost function. As long as I can calculate its gradient with respect to whatever parameters, I can initialize my parameters and update them using the gradient descent or its variations, and I will have my model, optimal model. Okay, so in the next video we are going to actually implement a simple linear regression model using this gradient tape, or to be more precise, implementation of estimation of parameters for linear regression using the gradient tape in next video.